Imagine humanity 1,000 years from now. 1,000 years of scientific progress, 1,000 years of engineering marvels, 1,000 years of dreams reaching upward into the cosmos. Now imagine that despite all of this, despite fusion reactors humming with the power of stars, despite artificial intelligence solving equations we cannot yet conceive, despite generation ships the size of cities, humanity remains exactly where it is today. Confined, bound, trapped within the gentle sphere of our solar system like insects in amber, forever gazing at distant lights we can see but never touch. This is not science fiction. This may be our reality. Tonight, we will explore a truth that space agencies whisper about in private, that physicists understand but rarely speak aloud, that the general public has not yet begun to accept. Interstellar travel, the journey between stars, may not be difficult. It may not be expensive. It may not be a question of when, but a question of never. The universe may have built an invisible prison around every solar system, and the bars of that prison are not made of steel or force fields. They are made of distance, energy, time, and the unforgiving laws of physics themselves. We have been told that space is the final frontier, that humanity's destiny lies among the stars. But what if we have been lied to, not by malice, but by optimism? What if the distances between stars are not merely vast, but cosmically, intentionally, impossibly insurmountable? What if every dream of reaching Alpha Centauri, of touching the worlds of distant suns, of spreading across the galaxy is nothing more than a beautiful fantasy, a story we tell ourselves to avoid confronting the truth that we are alone, not alone in the universe, but alone in our corner of it, forever. Space is not empty. It is filled with obstacles, each one designed as if by some cosmic architect to keep us exactly where we are. Tonight, we will journey through 6 insurmountable barriers that stand between humanity and the stars. The tyranny of distance so extreme that human language struggles to contain it. The energy problem that makes interstellar travel require more power than our civilization can generate. The hostile void that transforms space into an active killer. The time dilation paradox that turns relativity itself into a form of cosmic cruelty. The sustainability impossibility that reveals closed-loop systems as mathematical fiction. And finally, the weight of all these truths combined, the final verdict that our solar system may be humanity's forever home. But do not despair. There is strange comfort in limitation, profound peace in acceptance. To understand why we cannot leave is to understand our place in the universe with clarity and humility. It is to see our solar system not as a prison, but as a garden, vast and intricate, containing worlds enough for 1,000 lifetimes of exploration. Perhaps we were never meant to scatter among the stars. Perhaps we were meant to thrive here, to perfect our existence within the boundaries given to us, to become masters of our own cosmic neighbourhood before dreaming of others. If you have ever wondered whether humanity will truly become an interstellar species, whether your descendants will walk beneath alien suns, then this journey is for you. If you have ever felt the pull of the stars and wondered why we have not yet answered their call, stay with us. The answers lie ahead, not in hope or dreams, but in the mathematics of reality itself. And I promise you, what we discover together will change how you see every point of light in the night sky. Before we begin, I invite you to become part of this journey. Please, take a moment to comment below. Tell us where in the world you are watching from and what time it is in your corner of Earth. Are you watching as dawn breaks over your city, as twilight settles across your countryside, or perhaps in the deep hours of night when the rest of your world sleeps and you find yourself alone with your thoughts and the glow of your screen? We would love to know. This journey across cosmic truths is better travelled together, and your presence here now makes it real. If you find value in these explorations, if you appreciate journeys that trade spectacle for substance, hurry for patience, Please consider liking this video and subscribing to this channel. It helps us continue creating these long-form meditations on science, space, and the nature of our existence. Now, settle in. Let your breathing slow. Release the tensions of your day. We're about to drift into deep waters, into truths both frightening and strangely beautiful. We will not rush. We will not shout. We will simply follow the evidence wherever it leads, gently, carefully, like astronomers tracing the path of light that has travelled for eons just to reach our eyes. The cosmic prison awaits our understanding, but first we must learn to see its walls, invisible walls built not by intent but by the simple, unbreakable architecture of physics itself. Let us begin. We return now to a fundamental truth that shapes every moment of our cosmic imprisonment: distance. Not the distance between cities, or even between continents, but distance measured on a scale so vast that human minds simply were not evolved to comprehend it. As we drift back from Saturn's rings, as we watch the sun grow brighter behind us, we must confront an uncomfortable reality. Our solar system is not a prison because of walls or barriers. It is a prison because of the incomprehensible void that surrounds it. The distance between us and the nearest stars is not merely large. It is tyrannical. It is cruel. It is absolute. To understand this tyranny, we must begin with scale. Imagine for a moment that Earth is reduced to the size of a single grain of sand, a tiny speck barely visible between your fingertips. In this scale model, the moon would be another grain of sand about 2 inches away. The sun would be a small marble, roughly 8 feet distant. Already at this scale, our solar system begins to feel expansive. Mars would sit 15 feet away. Jupiter would be more than 40 feet from the sun. And Pluto, at the edge of our recognised solar neighbourhood, would rest over 300 feet away, the length of a football field. But now, the question that changes everything. In this same scale, where Earth is a grain of sand and our entire solar system spans the length of several football fields, how far away would the nearest star be? The answer is not comforting. Proxima Centauri, our closest stellar neighbour at 424 light-years away, would sit approximately 1,000 miles from our grain of sand Earth. That is the distance from New York to Kansas City, from London to Rome and back again. 1,000 miles of empty space containing nothing, to reach the very next point of light in the cosmic ocean. This is the tyranny of distance. This is the incomprehensible void. Let us make this more tangible. Let us calculate exactly how long it would take to reach Proxima Centauri, using various methods of travel, each one revealing the profound helplessness of our situation. If we were to drive to Proxima Centauri in an average car travelling at 60 miles per hour without ever stopping, the journey would take approximately 48 million years. 48 million years. Modern humans have existed for only 300,000 years. Civilization as we know it has existed for roughly 10,000 years. A road trip to the nearest star would span a time frame longer than the entire evolutionary journey from early primates to present-day humanity. Perhaps driving is too slow. What if we flew? A commercial airplane travels at roughly 500 miles per hour. At this speed, the journey to Proxima Centauri would take approximately 5.7 million years. Millions of years aboard an aircraft. Millions of years watching the stars barely shift position in the window. Time enough for entire species to evolve and go extinct on Earth. Time enough for continents to drift across the globe and reshape themselves. Time enough for mountains to rise and erode into dust. But we're not limited to cars and planes. We have rockets. Surely our fastest spacecraft can do better. The Parker Solar Probe, one of the fastest objects ever built by human hands, reaches speeds of approximately 430,000 miles per hour when diving close to the sun. At this astonishing velocity, faster than anything we have ever achieved, the journey to Proxima Centauri would still take over 6,700 years, 67 centuries. This is longer than all of recorded human history. The Parker Solar Probe, if aimed at Proxima Centauri today, would arrive in the year 8700 AD. The ancient Egyptians built their pyramids less than 5,000 years ago. This spacecraft would be travelling more than twice that long. Even this does not capture the full horror of the distance. Let's imagine something impossible. Let us imagine we could travel at the speed of light itself, the cosmic speed limit, the fastest velocity allowed by the laws of physics. At 186,282 miles per second, light crosses the distance from Earth to the Moon in just over 1 second. It reaches the Sun in 8 minutes. Surely at light speed the stars become accessible, and yet, even travelling at this impossible velocity, Proxima Centauri is still 4.24 years away. 4 years and 3 months of continuous travel at the fastest speed the universe permits. No slowing down, no stopping. Just 4 years of moving at a velocity so extreme that time itself begins to dilate and space begins to contract. To understand a light year is to accept that the universe operates on timescales that mock human existence. A light year is the distance light travels in 1 year, roughly 5.1 trillion miles. When we look at Proxima Centauri through a telescope, we are not seeing the star as it is now. We are seeing it as it was 4.4 years ago. The photons entering our eyes left that star before the last presidential election, before the pandemic, before countless moments of personal history. Those photons have been travelling through the void while we lived entire chapters of our lives, and they have only just arrived. Consider this. The light we see from some stars left those distant suns when dinosaurs still walked the earth. Photons that began their journey 65 million years ago, when Tyrannosaurus rex hunted beneath alien skies, are only now reaching our telescopes. Those stars may no longer exist. They may have exploded, collapsed, or faded into darkness millennia ago, but we still see them shining because their ancient light has not yet finished its journey across the void. We are not looking at the universe as it is. We are looking at a ghost, an echo, a museum of light preserved across incomprehensible time. This is not merely distance. This is temporal isolation. We are separated from the stars not just by space, but by time itself, locked into a universe where even information, travelling at the maximum possible speed, takes years to arrive. And if information takes years, what hope does matter have? What hope do we have? Even if we could somehow achieve light-speed travel, which we cannot, the journey to even the nearest stars would transform space exploration into something unrecognisable. Multi-generational travel would not be a choice. It would be an inevitability. A crew leaving Earth for Proxima Centauri at light speed would arrive 4 years older, but due to time dilation, far less time would pass for them than for those left behind on Earth. Yet even this relativistic gift cannot save us from the psychological horror of such a journey. Imagine departing Earth, knowing that everyone you left behind will age, change, perhaps die before you return. Imagine the isolation, the separation, the irreversible severance from everything you have ever known. Now imagine a more realistic scenario. If we travelled at even 1/10 the speed of light, an achievement far beyond our current capabilities, the journey to Proxima Centauri would take over 42 years, an entire human lifetime spent in transit. Children born aboard the spacecraft would grow old and die without ever setting foot on a planet. The psychological toll of such confinement is beyond measure. Studies of isolated populations, from Antarctic research stations to submarines, reveal that even months of isolation can lead to profound mental strain. Years of isolation, decades of it, with no hope of rescue, no possibility of turning back, would break the human spirit in ways we cannot predict. Multi-generational starships, often romanticized in science fiction, represent not adventure but tragedy. Imagine being born aboard a vessel travelling between stars, knowing that you will never see Earth, never breathe unfiltered air, never stand beneath an open sky. Your entire existence is a hallway, a corridor, a series of sealed chambers hurtling through darkness. Your purpose is not to explore, but simply to survive long enough to produce the next generation, who will do the same, who will pass the burden to their children, and so on, for lifetimes stacked upon lifetimes. This is not exploration, this is exile. Let us quantify this exile in the currency of human life. If we assume a human lifespan of 80 years, and we travel to Proxima Centauri at 1/10 light speed, the journey requires approximately half a human lifetime. But Proxima Centauri is merely the closest star. It may not have habitable planets. It may not have resources. It may offer nothing but another point of light in the darkness. To reach other potentially interesting star systems, the numbers become even more unforgiving. Tau Ceti, 12 light-years away, would take over a century at 1/10 light speed. 2 human lifetimes, Epsilon Eridani, 10.5 light-years distant, would require a similar span. Even at relativistic speeds, the human cost is measured not in years, but in generations lost to the void. And this brings us to the cruelest mathematical reality of all. Even our farthest ambassadors, the Voyager probes, those twin spacecraft launched in 1977 to explore the outer planets, have barely begun to scratch the surface of interstellar space. Voyager 1, the most distant human-made object, is currently over 15 billion miles from Earth, travelling at roughly 38,000 miles per hour. This sounds impressive until we calculate how long it would take Voyager 1 to reach Proxima Centauri at its current speed. The answer is approximately 73,000 years. 73,000 years to reach the nearest star. Voyager 1 has been travelling for over 45 years and has covered less than 1/10 of 1% of the distance to Proxima Centauri. It is not even close. It will never be close. In the time it would take Voyager to reach another star, human civilization could rise and fall dozens of times over. The Voyager probes carry golden records, discs engraved with sounds and images of Earth, messages intended for any intelligent life that might one day encounter them. These records contain greetings in 55 languages, music from across human cultures, and images of our world. They are time capsules, messages in bottles cast into an ocean so vast that they will drift for millennia before encountering anything at all. If, by some miracle, an alien civilization discovers one of these probes millions of years from now, humanity may no longer exist. They will find only a relic, a memorial to a species that once looked at the stars and dared to dream of reaching them. The Voyager probes are not harbingers of human expansion. They are epitaphs. They are proof not of our reach, but of our limits. They travel through a void so immense that their entire journey, everything they have accomplished, every planet they have photographed, every discovery they have made represents a distance so insignificant on the galactic scale that it barely registers. If the Milky Way galaxy were a map of the United States, Voyager 1 would have travelled roughly the width of a single human hair from the edge of the map, one hair's width. That is how far we've gone. That is how far we will ever go. This is the tyranny of distance. It is not merely an obstacle, it is a fundamental law of our existence. The universe has placed the stars just far enough away that reaching them is functionally impossible. We can see them. We can study their light. We can dream of visiting them, but we cannot touch them. The void is too great. The distance is too vast. The time required too long. Even light, which crosses the cosmos effortlessly, takes years to traverse the gulfs between stars. And we are not light. We are matter, bound by mass, by energy, by the cruel arithmetic of physics that dictates every journey, every hope, every desperate plan to escape our solar system must ultimately fail. As we drift back toward the inner solar system, back toward the warmth of the sun and the familiar glow of Earth, we carry with us this knowledge. The stars are not destinations, they are illusions of possibility, forever visible, forever out of reach. We are not travellers in a vast universe. We are prisoners in a cosmic cell, staring through bars made of distance, watching a universe we can observe but never touch. And the walls of this prison are not made of stone or steel. They are made of light years, of voids, of incomprehensible space that stretches beyond all human endurance. This is our reality. This is the tyranny of distance, and it is absolute. Beyond the rings of Saturn, beyond the ice giants and the scattered remnants of comets at the solar system's edge, lies a boundary far more formidable than distance alone. It is not measured in miles or astronomical units. It is measured in energy, raw, unimaginable quantities of power that dwarf anything humanity has ever produced or even conceived. To leave our solar system is not merely a question of travelling far, it is a question of harnessing forces so vast that they challenge the very laws of physics themselves. The energy problem is not abstract. It is mathematical, absolute, and unforgiving. As we contemplate journeys beyond our cosmic neighbourhood, we must confront a truth that no amount of optimism can diminish. We simply do not have enough power. Not now, not in the foreseeable future, perhaps not ever. Let us begin with numbers, cold and precise. To reach even the nearest star, Proxima Centauri, located 4.24 light-years away, a spacecraft would need to travel at a significant fraction of the speed of light, not to arrive quickly, but to arrive at all within a human lifetime. Consider what it means to accelerate even a small spacecraft, perhaps 1,000 kilograms, roughly the mass of a compact car, to just 10% of light speed. This is 30,000 kilometers per second, a velocity so extreme that Earth's fastest spacecraft would seem frozen by comparison. The kinetic energy required for this acceleration can be calculated with elegant simplicity. The formula is 1/2 mass multiplied by velocity squared. For our modest spacecraft, the result is staggering, approximately 4.5 times 10 to the 20th joules. This number is difficult to grasp in isolation, so let us translate it into terms we understand. This single spacecraft, this 1,000 kilogram vessel, would require more energy than humanity currently produces in an entire year. Every power plant, every solar panel, every burning fuel source on Earth combined produces roughly 5.8 times 10 to the 20th joules annually. We would need to channel nearly all of civilization's energy output for 12 months into accelerating a single small craft, and that is only to reach 10% of light speed, a velocity that would still require over 40 years to reach the nearest star. But the problem deepens. This calculation assumes perfect efficiency, that every joule of energy translates directly into forward motion with no loss whatsoever. In reality, no engine is perfectly efficient. Rocket engines, ion drives, even theoretical fusion propulsion systems lose energy to heat, to exhaust, to the fundamental limitations of thermodynamics. When we account for realistic efficiency rates, the energy requirement multiplies exponentially. A spacecraft using conventional chemical propulsion would require not just years of global energy output, but centuries, perhaps millennia. This is where the Tsiolkovsky rocket equation enters our story, a mathematical truth discovered over a century ago that continues to haunt every engineer who dreams of the stars. The equation describes a cruel reality. The faster you want to go, the more fuel you must carry. But fuel has mass, and that mass must also be accelerated, which requires more fuel, which adds more mass, which requires still more fuel. This cycle spirals into impossibility. To achieve high velocities using conventional propulsion, the mass of fuel quickly dwarfs the mass of the spacecraft itself by factors of thousands, millions, or worse. For example, to accelerate our 1,000 kilogram spacecraft to just 10% of light speed using the most efficient chemical rockets ever developed, we would need a fuel mass ratio so extreme that the fuel tank alone would exceed the mass of entire planets. The numbers become absurd, almost comical. if they were not so devastating to our dreams. Chemical propulsion, the technology that carried us to the moon, becomes laughably inadequate for interstellar space. The equation does not bend. It does not compromise. It simply states what is and what cannot be. So we look to alternatives. Nuclear propulsion has long been proposed as the solution to the energy problem. Nuclear fission and fusion reactions release energy millions of times more efficiently than chemical combustion. A small amount of nuclear fuel contains energy equivalent to thousands of tons of conventional rocket propellant. Project Orion, conceived in the 1950s, imagined a spacecraft propelled by nuclear explosions, bombs detonated behind a massive pusher plate, each blast accelerating the craft forward in pulses of raw atomic power. The concept was abandoned not because of physics, but because of politics, the test ban treaty, the fears of contamination. Yet even if we revived such designs, the energy problem remains daunting. Nuclear fusion, the holy grail of propulsion, promises even greater efficiency. Fusing hydrogen into helium releases energy at rates approaching what stars themselves produce. A fusion rocket could theoretically achieve velocities of 10 to 20% of light speed, making interstellar travel conceivable within multiple human lifetimes. Yet despite decades of research, we have not successfully created a sustained fusion reaction that produces more energy than it consumes here on Earth, let alone in the hostile environment of space. Fusion remains perpetually decades away, a dream deferred, a solution that glimmers on the horizon but never arrives. And even if we mastered fusion, the energy requirements remain staggering. Accelerating our modest spacecraft would still demand fuel measured in tons, perhaps hundreds of tons, all carried from Earth or harvested from asteroids, refined, processed and loaded aboard. The infrastructure required to build, fuel and launch such a vessel would rival the entire industrial capacity of modern civilization. Then there is antimatter, the most energy-dense substance theoretically possible. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, precisely as Einstein's equation, E equals mc squared, predicts. A single kilogram of antimatter reacting with a kilogram of matter releases 1.8 times 10 to the 17th joules, enough energy to power the entire United States for several days. With antimatter, we could achieve velocities approaching significant fractions of light speed without the crushing fuel mass ratios of conventional rockets. But antimatter does not exist naturally in quantities we can harvest. This must be manufactured particle by particle in massive accelerators like CERN. Currently humanity produces only a few nanograms of antimatter per year, at costs exceeding tens of trillions of dollars per gram. To fuel a single interstellar journey would require kilograms, perhaps tons of antimatter. The energy required to produce this antimatter exceeds, by orders of magnitude, the energy the antimatter itself would provide. It is a cosmic irony. To travel to the stars using antimatter, we would first need to harness the energy output of stars themselves just to create the fuel. Even if we solved production, containment presents its own nightmare. Antimatter cannot touch normal matter without instantly annihilating. It must be suspended in magnetic fields within perfect vacuums. A containment failure would not merely be an accident, it would be an explosion rivaling nuclear weapons. Carrying tons of antimatter through space is carrying the potential for catastrophic detonation with every moment of the journey. Solar sails offer an elegant alternative, propulsion without fuel. A vast reflective sail, kilometres across, catches photons from the sun, each particle of light imparting a tiny push. Over time, these pushes accumulate, gradually accelerating the spacecraft. Solar sails require no onboard fuel, no engines, no complex machinery. They are passive, simple, almost poetic in their design. Yet they too are bound by energy limitations. The pressure exerted by sunlight is extraordinarily weak. To achieve meaningful acceleration, sails must be immense. structures so large they would be visible from Earth's surface, gossamer membranes stretching across the void. Even then, acceleration is glacial. A solar sail might take decades to reach velocities sufficient for interplanetary travel, and centuries to approach speeds necessary for interstellar journeys. Moreover, sunlight weakens with distance. Beyond the orbit of Mars, the sun's pressure diminishes rapidly. By the time a solar sail reaches the outer solar system, acceleration slows to nearly nothing. Laser propulsion, a variation on this concept, proposes using ground-based or orbital lasers to push sails with concentrated beams of light far more powerful than sunlight alone. This could, in theory, accelerate spacecraft to substantial fractions of light speed, but the lasers themselves would require power outputs measured in gigawatts or terawatts, sustained for months or years. We return once again to the energy problem. To push a spacecraft toward the stars, we must first build laser arrays consuming more power than the entire nations, focusing that energy with perfect precision across millions or billions of miles. Beyond propulsion lies another insurmountable challenge: energy storage. Every spacecraft must carry power not just for acceleration, but for life, support, navigation, communication, course corrections. These systems must function for decades, perhaps centuries. Batteries, even the most advanced lithium-ion or solid-state designs, degrade over time and carry insufficient energy density. Solar panels become useless as the spacecraft moves beyond the reach of the sun's light. Nuclear reactors could provide long-term power, but they add mass, require maintenance, and eventually deplete their fuel. The concept of energy return on energy invested becomes critical here. For any journey to be practical, the energy gained from reaching the destination must somehow exceed, or at least justify, the energy expended to get there. On Earth, we drill for oil because the energy we extract exceeds the energy required to extract it. But what energy can we extract from interstellar space? What resource justifies the expenditure of civilization's entire energy output for a single journey? There is no oil between the stars, no minerals we cannot find in our own solar system, no tangible return on investment that makes energetic sense. This is where thermodynamics becomes not just a challenge, but a philosophical barrier. The second law of thermodynamics states that entropy, disorder, always increases in a closed system. Every energy conversion loses some energy to waste heat. Every engine, every reaction, every process operates below 100% efficiency. The energy cost of interstellar travel, when calculated honestly, may simply exceed any plausible benefit. The universe is not designed for convenience. It does not owe us access to other stars. Some propose harvesting the energy of entire stars through structures like Dyson spheres, massive arrays of solar collectors encircling a sun, capturing nearly all of its radiated energy. A Dyson sphere around our sun could theoretically harness 3.8 times 10 to the 26th watts, 1,000,000 times more energy than currently available to humanity. Surely with such power, interstellar travel becomes trivial. But even a Dyson sphere may not suffice. To establish routine interstellar travel, to send not one spacecraft but fleets, to create supply lines and communication networks across light years, would require energy expenditures so vast that even stellar-scale power sources might prove inadequate. Consider a single star's energy output captured entirely might accelerate perhaps a few dozen spacecraft to meaningful interstellar velocities per year. This is not the vibrant spacefaring civilization of science fiction. It is a trickle, a handful of vessels crawling across centuries of darkness. Moreover, building a Dyson sphere itself requires energy and resources on scales we can barely imagine. Mining entire planets, constructing trillions of solar panels, positioning them in stable orbits, all of this demands an industrial capacity that assumes we have already solved the energy problem. It is circular reasoning. We need vast energy to leave the solar system, but we need to leave the solar system to access the resources necessary to generate vast energy. The energy problem is not one we can engineer around with cleverness or determination. It is woven into the fabric of physics itself. The speed of light is not merely fast, it is the cosmic speed limit, and approaching even a fraction of it demands energy on scales that dwarf human comprehension. The universe is vast, and that vastness is enforced by energy requirements so extreme they border on prohibition. As we drift here in thought, contemplating the distances between stars, we must accept a humbling truth. Energy is not just a resource, it is the currency of the cosmos, and we are impoverished beyond measure. We can dream of warp drives and wormholes, of technologies yet undiscovered that bypass these limitations, but dreams are not physics, hope is not energy. The equations remain indifferent to our ambitions. To leave our solar system, to truly travel among the stars as casual voyagers rather than desperate pioneers, we would need to become something we are not. We would need to command energies that only stars themselves possess. We would need to rewrite the laws that govern motion, mass, and momentum. Perhaps one day, centuries or millennia hence, our descendants will find pathways we cannot imagine, loopholes in physics we have not yet discovered. But for now, in this moment, with our current understanding and our limited power, the stars remain beyond reach, not because we lack courage or curiosity, but because we lack something far more fundamental. We lack the energy to break free from the cosmic prison we call home. The universe has set the terms of travel, and those terms are denominated in quantities of power we cannot pay. Ahead of us, the void stretches endlessly, filled not with opportunity, but with obstacles measured in joules and watts. And as we calculate, as we run the numbers again and again, hoping for different results, the answer returns unchanged. We simply do not have enough power. We never have. Perhaps we never will. Beyond the beauty of Saturn's rings, beyond the majesty of Jupiter's storms, lies a truth we often overlook in our cosmic wonder. Space is not simply empty. It is hostile. It is not merely indifferent to human life. It is actively, relentlessly trying to end it. We speak of the void as if it were nothing, a vacuum, an absence. But this characterization is dangerously incomplete. The space between worlds is filled with invisible threats, each one capable of ending a mission, destroying a spacecraft, or extinguishing human life with silent efficiency. To journey beyond our solar system is not just to travel far. It is to expose ourselves to an environment so fundamentally opposed to biological existence that every moment becomes a battle against entropy, radiation, and the slow mechanical death of everything we build. The first enemy is invisible, yet omnipresent. Cosmic radiation permeates the void like an ocean of death we cannot see or feel until it is too late. Unlike the relatively gentle radiation from our sun, which Earth's magnetic field deflects like an invisible shield, cosmic radiation comes from all directions. Supernovae that exploded millions of years ago, neutron stars spinning at incomprehensible speeds, and galactic events beyond our understanding all contribute to this constant bombardment. High-energy protons and heavy ions tear through space at nearly the speed of light, and they do not stop for spacecraft hulls or human tissue. On Earth, we are protected. Our atmosphere absorbs most of this radiation. Our magnetosphere deflects it. Even on the International Space Station, astronauts orbit within the protective embrace of Earth's magnetic field. But beyond the heliosphere, the bubble of charged particles that extends from our sun, there is no protection. A journey to another star system would expose travellers to cumulative radiation doses that increase not linearly, but exponentially with time. Consider the mathematics of exposure. A journey lasting decades or centuries means that every cell in the human body would be struck repeatedly by high-energy particles. DNA strands would be severed, chromosomes shattered, repair mechanisms overwhelmed. cancer becomes not a risk, but a certainty. Neurological damage accumulates, cognitive function degrades. The very biological machinery that makes us human begins to fail, cell by cell, year by year. Shielding helps, but only to a point. Lead, water, polyethylene all provide some protection, but the mass required to shield against cosmic radiation for centuries would make the spacecraft impossibly heavy. We would need walls meters thick, adding millions of tons to a vessel that must already carry everything needed for survival across unimaginable distances. And it is not just human bodies that suffer. Cosmic radiation degrades spacecraft systems with equal indifference. Electronics are fried by single-event upsets, where a single particle strikes a critical component and causes catastrophic failure. Solar panels lose efficiency as their molecular structure is disrupted. Computer memory becomes corrupted. The very materials of the spacecraft become brittle and weak as radiation damage accumulates at the atomic level. A vessel that launches in perfect condition will, over decades, become a deteriorating shell of its former self, its systems failing one by one in a slow cascade toward inevitable collapse. But radiation is only the beginning. The void is filled with matter, and that matter is travelling at velocities that transform the tiniest fragments into devastating weapons. Micrometeoroids, particles smaller than grains of sand, drift through space at speeds reaching tens of thousands of miles per hour. At these velocities, mass becomes irrelevant. Kinetic energy is everything. A speck of dust striking a spacecraft at orbital velocities doesn't bounce off. It vaporizes on impact, releasing energy equivalent to a small explosive. The impact site becomes a crater. Hull integrity is compromised. A particle the size of a pebble could punch through multiple layers of shielding and tear through critical systems before anyone realizes what has happened. Unlike Earth's atmosphere, which burns up most small debris before it reaches the ground, space offers no such protection. Every fragment, every ice crystal, every microscopic piece of rock is a potential threat. And they are everywhere. The space between planets is littered with debris from billions of years of collisions, comet tails and pulverized asteroids. The space between star systems contains the scattered remains of ancient stellar deaths, dust clouds, and matter ejected from planetary formation. A journey lasting centuries means billions of opportunities for catastrophic impact. Engineers have designed spacecraft with Whipple shields, layered barriers that absorb impacts by vaporizing incoming particles before they reach critical systems. But these shields add mass, and they can only protect against particles of limited size. Larger debris requires active detection and maneuvering, which consumes fuel and energy we cannot spare on an interstellar journey. And what happens when a shield is damaged? There is no harbour to pull into for repairs, no dock where replacement parts await. Every impact weakens the vessel permanently. The threat extends beyond individual particles. In our own orbital space around Earth, we face the spectre of Kessler syndrome, a cascading collision scenario where debris strikes satellites, creating more debris, which strikes more objects, creating an exponentially growing cloud of high-velocity fragments that makes entire orbital regions unusable. Now, imagine this phenomenon on an interstellar scale. The space between stars may contain debris fields from ancient collisions, clouds of fragmentary matter that we cannot detect until we are already within them. Travelling at a significant fraction of light speed, even a sparse debris field becomes a gauntlet of destruction. Each particle impact releases heat and energy. Each collision creates fragments that damage other systems. A spacecraft could be slowly shredded by thousands of tiny impacts, death by 1,000,000 cuts played out across the dark between the stars. Then there is the thermal nightmare. Space is often described as cold, and in one sense this is true. The temperature of the cosmic background radiation is only 2.7 degrees above absolute zero. But temperature in space is not experienced the way it is on Earth. Without an atmosphere to conduct heat away, Thermal management becomes a delicate balancing act between freezing and overheating. A spacecraft generates heat from its systems, from its reactor, from the bodies of its crew. This heat has nowhere to go except through radiation, a slow and inefficient process. On the shadowed side of a vessel, temperatures plummet. On the sun-facing side, they soar. The differential creates stresses that warp materials, crack joints, and compromise seals. Over years, these temperature cycles accumulate. Metals expand and contract. Composites delaminate. Lubricants freeze or vaporize. Every component designed on Earth, tested in Earth-like conditions, must somehow continue functioning through temperature extremes it was never designed to endure, for time spans far exceeding any laboratory test. We cannot adequately simulate decades of thermal cycling. We cannot predict which systems will fail first, or how their failure will cascade into others. The spacecraft becomes a slow-motion experiment in material science, where failure is not a question of if, but when. Mechanical degradation haunts every system. Bearings wear, seals crack, pumps fail. On Earth, maintenance is constant. Equipment is inspected, replaced, upgraded. But on an interstellar vessel, every replacement part must be carried from the beginning or manufactured from limited raw materials. There is no supply chain, no next-day delivery. When a critical component fails and no spare exists, the mission ends. The cruel mathematics of reliability become unavoidable. If a system has a 99.9% reliability over 1 year, its reliability over 100 years drops dramatically. Compound this across thousands of systems, each with its own failure rates, and the probability of mission success approaches zero. We have never built anything designed to function autonomously for centuries. Our longest operating spacecraft, the Voyagers, have been travelling for over 4 decades, and they are already failing. Systems are shutting down, power is fading. They were designed for a specific mission duration, and they have exceeded it admirably. But they are not life support systems. They carry no crew. They are simple compared to what an interstellar vessel would require. The complexity required for human survival, the redundancy, the life support, the food production, the waste recycling, all of this represents millions of potential failure points, each waiting to cascade into catastrophe. And then there is the silence, the crushing, endless silence of the void. Communication delays become not minutes, as with Mars, but years. A distress signal sent from halfway to Proxima Centauri would take over 2 years to reach Earth, and another 2 years for any response to return. By the time help could even be acknowledged, the crisis would have long since resolved itself through survival or death. A crew would be utterly, completely alone, aware that no rescue is possible, no guidance can arrive in time to matter, no communication can provide comfort when it takes years to hear a reply. The psychological toll of this isolation is difficult to overstate. Humans evolved in social groups surrounded by the immediate feedback of community. Astronauts on the ISS can see Earth from their window. They can speak with mission control in real time. They know their mission will end, that they will return home. But an interstellar crew would watch Earth become a star, then fade into the general scatter of the Milky Way. They would know, with absolute certainty, that they will never return. That everyone they knew before departure is aging, dying, becoming history while they drift in an aluminum coffin through an ocean of nothing. Sensory deprivation becomes inevitable. The same walls, the same faces, the same recycled air, the same tasteless food, day after day, year after year. There is no weather, no seasons, no variety, except what can be artificially created. The human mind craves novelty, change, stimulation. Deprive it of these and psychological breakdown follows. Depression, anxiety, interpersonal conflict, all amplified by the knowledge that escape is impossible. Confinement in a submarine or polar research station ends after months. Confinement on an interstellar vessel ends only with death or arrival decades away. Multi-generational crews face even darker questions. Children born in transit will never know Earth. They will inherit a mission they did not choose, sentenced to serve as biological components in a machine designed by ancestors they never met. What psychological damage comes from knowing you were born to be a caretaker of systems, that your entire existence is defined by maintenance schedules and duty rosters? What happens when a generation decides they no longer consent to continue the journey? Mutiny is not just a possibility. Over centuries it becomes a probability. And in the void, there is no authority to appeal to, no external force to maintain order. The social dynamics of the crew become the entire universe, and that universe will inevitably fracture under the pressure of time and isolation. We cannot adequately prepare for these scenarios because we have never faced them. Our longest space missions measure in months, not decades or centuries. We have never tested a closed-loop life support system for 100 years. We have never studied the psychological effects of true interstellar isolation. We have never built mechanical systems that must function without maintenance for generations. Every simulation, every analog study on Earth is fundamentally limited, because the participants know it will end, that they can leave, that Earth is just outside the door. The problems we would encounter in the true deep void are not just unknown, they are unknowable until experienced. We can predict radiation exposure, but not the subtle cumulative effects on complex biological systems over lifetimes. We can calculate impact probabilities, but not anticipate debris fields we've never detected. We can design redundant systems, but not foresee the cascade failures that emerge from complex interactions over decades. The engineering challenge is not difficult. It is impossible with our current understanding. Space does not wait for us to solve these problems. It does not pause while we research and develop solutions. It exists as it has for billions of years, indifferent to our presence, our plans, our hopes. The void is not evil. It is not intentionally hostile. It simply exists according to physical laws that make biological survival extraordinarily difficult. And every kilometre we travel from Earth multiplies these difficulties exponentially. To leave our solar system is to enter an environment where everything, from the smallest particle to the largest cosmic ray, conspires against human survival, where time itself becomes an enemy as systems degrade and crews age and hope fades into the endless dark, where the silence is so complete that it becomes a physical presence, pressing down on consciousness until madness seems preferable to another day of identical routine. This is the hostile void, not empty, but filled with invisible deaths, not silent, but screaming with radiation we cannot hear, not peaceful, but waging a relentless war against every bolt, every wire, every cell that dares intrude upon its domain. And it is a war we cannot win, because the void has infinite patience, and we do not. The void has no systems that fail, no resources that deplete, no morale that breaks. It simply exists and waits, and slowly, inevitably, grinds down everything we send into its depths. Beyond the challenges of energy and the hostility of the void lies a trap written into the very fabric of reality itself. Time dilation is not just a theoretical curiosity discussed in physics classrooms. It is a fundamental cruelty encoded in the structure of space-time, one that transforms the dream of interstellar travel into a philosophical nightmare. Even if we could build ships capable of approaching the speed of light, even if we could somehow survive the journey across the cosmic gulf, we would discover that the universe has one final barrier, not of distance or energy, but of time itself. This barrier does not merely slow us down, it severs us permanently from everything we know, everyone we love, and the very civilization that sent us forth into the darkness. Time, we have learned, is not universal. It does not tick at the same rate everywhere in the universe. Einstein's theory of special relativity revealed a truth both elegant and horrifying. As an object approaches the speed of light, time itself slows down for that object relative to the rest of the universe. This is not an illusion or a measurement error, it is reality. A clock moving at near light speed genuinely ticks more slowly than a stationary one. And for travellers aboard such a vessel, the implications are not merely scientific, they are existential. Consider the classic thought experiment known as the twin paradox. One twin boards a spacecraft capable of travelling at 90% the speed of light and journeys to a star 10 light-years away. From Earth's perspective, the trip takes roughly 22 years, 11 years there and 11 years back. But aboard the spacecraft, time passes differently. Due to time dilation, the travelling twin experiences only about 10 years of subjective time. When the traveller returns home, they step off the ship having aged a decade, only to discover their twin now 22 years older. Friends have moved on, parents may have passed away. The world has changed in ways subtle and profound. The traveller has become a visitor from the past, arriving in a future they did not live through. Now scale this up, not to nearby stars, but to destinations hundreds or thousands of light years away. The time dilation effect becomes catastrophic. A journey to a star 500 light years distant, travelling at 99.9% the speed of light, might feel like only 7 years to those aboard the ship. But on Earth, a millennium will have passed. Everyone the travellers knew will be dead. The language they spoke may have evolved beyond recognition. The nation that funded their mission may no longer exist. Entire eras of history will have unfolded in their absence. They will return, not as explorers, but as ghosts, as relics of an ancient age stepping into a world that has forgotten them. This is not simply loss, it is erasure. Time dilation transforms interstellar travellers into exiles, not from a place, but from time itself. They become unstuck from the continuity of human experience, drifting through epochs like shipwrecked sailors adrift on an ocean with no shore. Every light year travelled at relativistic speeds is a century surrendered, a generation abandoned. The faster you go, the more time you lose. The closer you approach the speed of light, the more completely you are severed from the timeline of humanity. But the cruelty deepens. Time dilation is not symmetrical in its effects. While travellers age slowly, the universe around them ages rapidly. Communication becomes nearly impossible. A distress signal sent from a relativistic ship, travelling at near light speed toward a distant star, would take decades or centuries to reach Earth. By the time a response is sent, the travellers may have already arrived at their destination, or perished in the void. There is no rescue mission possible. No resupply ship can catch up to a vessel already moving at relativistic speeds. The travellers are alone, not just in space, but in time. Every second they travel pushes them further into the future, further beyond the reach of anyone who might help them. And what of those left behind? Families wave goodbye, knowing they will never see their loved ones again, not because of distance, but because of time. Parents watch their children board a starship, aware that if the mission succeeds, those children will return centuries hence, younger than their own great-great-grandchildren. How does a civilization reconcile this? How do we send people into a future where they will be strangers, where their context, their culture, their very identity will be obsolete? The social fabric required for space exploration depends on continuity. We build upon the work of previous generations. We share knowledge, pass down wisdom, maintain institutions across decades and centuries. But time dilation obliterates continuity. A crew that departs in 2150 and returns in 2650, having experienced only 10 years subjectively, brings back data from a civilization 500 years dead. They report to governments that no longer exist. They speak to descendants who regard them as curiosities, historical artifacts animated by cruel physics. The mission, no matter how successful scientifically, is a human tragedy. Worse still is the paradox of the late arriving ship. Imagine we launch a generation ship in 2100, travelling at 10% the speed of light toward a star 50 light years away. The journey takes 500 years, but in 2200, just a century later, we develop faster propulsion technology. A new ship launches at 50% light speed and arrives at the same destination in just 100 years, centuries before the first ship. The original crew, if any descendants survive, arrive to find a thriving colony established by people who left Earth long after they did. Their sacrifice, their isolation, their suffering becomes pointless. They are not pioneers, they are anachronisms overtaken by history before they even arrived. This is the weight calculation problem. If technology is improving, it may always be better to wait before launching. Any mission sent today could be overtaken by a faster mission sent tomorrow, but waiting indefinitely means never going at all. Time dilation makes this dilemma even more painful. A crew travelling at relativistic speeds experiences the journey quickly, but arrives in a future where even faster ships may have already colonised the stars. They become permanent wanderers, perpetually arriving too late, their subjective experience of time rendering them obsolete. Physics offers no mercy here. Time dilation is a consequence of the speed of light being the ultimate speed limit. As a spacecraft accelerates closer to light speed, time slows more dramatically. At 99% the speed of light, time passes about 7 times slower for the travellers. At 99.9%, about 22 times slower. At 99.99%, over 70 times slower. But the energy required to reach these speeds increases exponentially, and the temporal cost becomes unbearable. A 10-year journey at 99.9% light speed could mean 1,000 years pass on Earth. The travellers effectively vanish from history, leaping forward across centuries in the blink of an eye. And what do they find when they arrive? Not the civilization they left, but its distant descendants, perhaps evolved beyond recognition. Humanity may have spread across the galaxy using technologies the travellers cannot comprehend, or perhaps humanity has gone entirely, replaced by artificial intelligences or new forms of life. The travellers, having sacrificed everything to cross the void, arrive in a universe where they are no longer relevant, where the questions they sought to answer have already been answered, where their journey itself is a forgotten footnote in some ancient archive. This is not exploration, it is banishment. Time dilation transforms interstellar travel into a one-way ticket not just through space, but through time. You do not return home, you cannot. Home exists only in the past, and the past is as unreachable as the stars themselves. Every relativistic journey is a kind of death, a severance from the flow of time that connects all human experience. The traveller lives, yes, but lives as a phantom, out of sync with the rest of humanity, watching the universe age in fast forward while their own subjective time crawls forward moment by moment. The philosophical weight of this is crushing. We are creatures of continuity. We form bonds across time, raising children who raise children who carry forward our stories, our values, our collective memory. Time dilation shatters this chain. It makes nomads of us, not just in space, but across the timeline itself. A crew that embarks on a relativistic voyage becomes a separate thread of human history, one that diverges permanently from the main timeline. They are not part of humanity's future. They are a parallel timeline intersecting briefly at departure and perhaps at arrival, but isolated and alone in between. This isolation extends beyond the emotional. It is practical, logistical, and absolute. If something goes wrong on a relativistic journey, help cannot arrive. If the ship is damaged, there is no rescue. If supplies run low, there is no resupply. The crew must be entirely self-sufficient, carrying with them everything they will ever need, because by the time any message reaches home and help is dispatched, centuries will have passed. The ship is not just distant in space, it is distant in time, drifting through decades and centuries as it crosses the void. It is a closed system, cut off not by distance alone, but by the relentless forward march of time dilation. Even communication becomes a haunting exercise. A message sent from a ship travelling at 90% light speed takes not just the light travel time to reach Earth, but arrives in an Earth years or decades older than when the message was sent. Conversations become impossible. Questions are asked and answered across generations. A child born on the ship might send a message to Earth, only for the response to arrive when that child is elderly, if they live that long. The dialogue becomes a correspondence between eras, a slow exchange across an unbridgeable temporal chasm. And what of the purpose of such journeys? We send ships to explore, to find new worlds, to search for life, to expand humanity's reach. But if those ships arrive centuries or millennia after they were launched, what remains of the mission's intent? The science they conduct may be obsolete by the time the data reaches Earth. The worlds they explore may have already been visited by others. The questions they seek to answer may no longer be questions at all. Time dilation makes even the goals of interstellar exploration uncertain, because the act of travelling transforms the travellers into time travellers, arriving in futures where their mission may no longer matter. This is the cruelty physics has woven into the fabric of reality. We are bound not just by distance, but by time. The faster we travel, the more we lose. The further we go, the more we are exiled from our own species. Time dilation is not a challenge to be overcome with better technology. It is a fundamental property of space-time, as unchangeable as the speed of light itself. We cannot engineer our way out of it. We cannot invent a technology that makes time pass equally for all observers. Time dilation is not a bug in the universe's code. It is a feature, and it is merciless. So we are left with a question that has no answer. What does it mean to explore a universe where exploration costs not just years of your life, but the entire lifetime of your civilization? What does it mean to reach for the stars when every light year travelled pushes you further into a future you cannot return from? The time dilation paradox is not just a problem of physics. It is a problem of meaning, of purpose, of what it means to be human in a universe that does not care about our timelines, our relationships, or our need to belong to a shared moment in history. Time dilation reveals a truth we do not want to face. The stars are not just far away. They are separated from us by an ocean of time as vast as the ocean of space. To cross that distance is to become something other than what we are, to surrender our place in the stream of human time and drift alone through ages we'll never truly be part of. It is to become travellers without a home, explorers without a destination that remains as we left it, voyagers on a journey that erases the very meaning of return. This is the final cruelty of interstellar travel. Even if we could go, we would lose ourselves in the going. Time dilation does not merely separate us from those we leave behind. It separates us from time itself, from history, from continuity, from everything that makes us part of a shared human story. In the end, the stars may be reachable, but at a cost too terrible to pay. Not in fuel, not in danger, but in time. The one resource we can never recover, and the one thing the universe will not let us keep. In the darkness between stars, a generation ship glides silently through the void, carrying thousands of souls toward a destination their great-grandchildren might never see. Inside, gardens bloom under artificial light. Water cycles through purification systems. Air is recycled, scrubbed, and breathed again. Everything appears perfect, a closed loop, a miniature Earth suspended in the infinite black. But perfection is an illusion. Deep within the ship's systems, entropy is working, patient and relentless. A water pump degrades slightly, a seal weakens, a crop begins to fail, and there is no resupply mission. No spare parts. Arriving from Earth, no rescue. The generation ship, humanity's greatest hope for reaching another star, contains within it a fundamental flaw that cannot be engineered away. True sustainability is not merely difficult, it is thermodynamically impossible. The dream of a self-sustaining spacecraft is as old as space travel itself. We imagine massive vessels, cities in space, carrying everything needed to sustain human life for centuries. But this dream collides with one of the most fundamental laws of the universe, the second law of thermodynamics. Entropy always increases. Order inevitably decays into disorder. Every closed system, no matter how perfectly designed, will eventually run down, break down, and fail. On Earth, we do not notice this because Earth is not a closed system. It receives a constant influx of energy from the Sun, 173,000 terawatts of power, bathing our planet every moment. This energy drives photosynthesis, weather patterns, ocean currents, the entire machinery of life. When something breaks, we can mine new materials. When crops fail, we plant others. When systems degrade, we rebuild them using resources continuously replenished by geological and biological processes spanning the entire planet. But in space, aboard a generation ship, there is no such luxury. Every atom of material must be carried from the beginning. Every component, every spare part, every ounce of redundancy adds mass, and mass requires energy to accelerate, to maintain course, to slow down upon arrival. The ship cannot be infinitely large. It cannot carry infinite resources. It must be a closed loop, recycling everything forever. And this is where the impossibility reveals itself. Perfect recycling does not exist. Every time water is purified, some is lost. Every time air is scrubbed, filters degrade. Every time metal is recycled, impurities accumulate. Entropy does not rest. It works constantly, invisibly, degrading seals, corroding pipes, weakening structures. Over years, these losses compound. Over decades, they become critical. Over centuries, they become catastrophic. We have attempted to create closed ecosystems before, and every attempt has taught us the same humbling lesson. Biosphere 2, constructed in the Arizona desert in the early 1990s, was humanity's most ambitious attempt to create a self-sustaining miniature Earth. Within its glass walls existed 7 distinct biomes: rainforest, ocean, wetland, savanna, desert, agricultural zones, and living quarters. 8 crew members sealed themselves inside for 2 years, attempting to prove that humans could survive indefinitely in a closed ecological system. The experiment was a disaster. Within months, oxygen levels began to drop. The concrete structure absorbed oxygen faster than the plants could produce it. Carbon dioxide spiked to dangerous levels. The crew struggled with hunger as crops failed repeatedly. Pollinators died off. Certain plant species became invasive, overwhelming others. 19 of 25 vertebrate species went extinct. Insects thrived, but not the ones needed for agriculture. Cockroaches and ants proliferated wildly. Most troubling was the discovery that they did not understand the system they had created. Complex interactions between microbes, plants, animals, and the physical structure produced unexpected cascading effects. When one variable changed, everything changed. The system was not stable, it was not predictable, and critically, it was not sustainable. Oxygen had to be pumped in, food had to be brought in. After 16 months, the mission was compromised. After 2 years, the crew emerged, and the experiment was acknowledged as a failure. Biosphere 2 existed on Earth, with access to sunlight, gravity, atmospheric pressure, and the option to open a door if catastrophe struck. Imagine the same experiment, but in the void between stars, with no possibility of resupply, no emergency exit, no second chance. Even our space stations, the International Space Station and before it Mir, depend entirely on constant resupply from Earth. Every few months cargo ships arrive carrying water, food, spare parts, scientific equipment, and replacement components. The ISS does recycle water, recovering about 90% from humidity, urine, and other sources, but that remaining 10% must be replaced. Filters wear out, pumps fail, electronics degrade in the radiation-heavy environment of low Earth orbit. The station requires approximately 7,000 pounds of supplies per astronaut per year, even with recycling. Without resupply, the ISS would become uninhabitable within months. Life support would fail, water would run out, air scrubbers would stop functioning. And this is a station in low Earth orbit, just 250 miles above the planet, in constant communication, with rescue possible within hours. A generation ship to another star would be millions, perhaps billions of miles from any help, travelling for centuries with no possibility of resupply. The challenge extends far beyond environmental systems. Consider the human population itself. Genetic diversity is not optional for long-term survival. It is essential. Studies suggest that a minimum viable population for a multi-generational space voyage would be at least 500 individuals, some estimates suggest several thousand, to prevent genetic bottlenecking and inbreeding depression. This population must be carefully managed for genetic diversity across generations, but 500 people require food, water, air, living space, medical care, education, and governance. The ship must support not only those alive at launch, but their children, grandchildren, and great-grandchildren, populations that will fluctuate, age, require different resources at different life stages. If we assume 500 people as the absolute minimum, and each person requires a habitat volume similar to a small apartment, along with agricultural space, water recycling, air processing, waste management, manufacturing, facilities, hospitals, schools and recreational areas, the ship quickly becomes enormous. Conservative estimates suggest a minimum of 500,000 cubic metres of habitable space, equivalent to a structure several times larger than the largest ocean liner ever built. And this does not include fuel, engines, shielding or propulsion systems. The ship would need to be a mobile city, self-sustaining for centuries, and the larger it becomes, the more energy is required to accelerate it. The more systems need maintenance, the more points of failure emerge. Food production presents its own cascading challenges. Agriculture aboard a generation ship would rely on controlled environment farming, likely hydroponics or aeroponics. But crops fail. Disease spreads. A single pathogen in a closed environment can devastate an entire harvest. On Earth, farmers plant diverse crops across vast regions, buffering against localized failures. On a ship, space is limited. Crop diversity is constrained. A single failure could mean starvation. And crops require not just water and light, but nutrients, nitrogen, phosphorus, potassium, trace elements. These nutrients must be cycled from waste, both human and agricultural. But nutrient cycling is inefficient. Elements are lost, locked into forms that plants cannot access, or bound into structures that do not decompose quickly enough. Over generations, soils, or their hydroponic equivalents become depleted. Fertilizers must be synthesized. But synthesizing fertilizers requires energy and raw materials, both of which are finite aboard the ship. Worse, the ship cannot afford a single point of failure. Redundancy is essential, but redundancy adds mass and complexity. If the primary air scrubbing system fails, backups must activate, but backups also fail, and who repairs them? The crew must possess not only the knowledge but the tools and materials to manufacture replacement parts. This requires machine shops, raw materials, metallurgical facilities, electronics fabrication. The ship must carry the infrastructure to rebuild itself, continuously, forever. But tools wear out, machines degrade, and knowledge, critically, can be lost. Maintaining technical knowledge across generations is a challenge civilizations have struggled with throughout history. The generation born on the ship will not remember Earth. They will know only the ship, its corridors, its systems, its endless hum. Their children will inherit technical manuals, training programs, and oral traditions, but will they understand them? Will they care? The 15th generation, born into a metal world they never chose, may begin to question the mission itself. Why are we travelling to a star we will never see? Why maintain systems for a destination that exists only in stories? When the stakes are abstract and the labour is immediate and exhausting, social cohesion fractures. History is filled with societies that forgot essential knowledge, that abandoned technologies their ancestors mastered, not because it was impossible, but because the will to continue vanished. Social collapse aboard a generation ship is not a matter of if, but when. Multi-generational isolation in a confined environment breeds psychological strain. Conflict over resources, governance, reproduction rights and labour allocation becomes inevitable. Factions form. Authority is questioned. If a crisis occurs, a crop failure, a disease outbreak, a major system malfunction, and the population perceives leadership as incompetent, rebellion is possible. A single violent conflict aboard a generation ship could be catastrophic. There is no place to flee, no neutral ground, no external authority to mediate. And if critical systems are damaged during conflict, if engineers are killed, if knowledge is lost, the ship becomes a tomb drifting through the void, its destination irrelevant. Even assuming perfect social cohesion, perfect knowledge transmission and perfect maintenance, the ship still faces an unsolvable problem. It cannot be truly self-sufficient. Manufacturing advanced electronics, for example, requires rare earth elements, precision fabrication, clean rooms, and expertise that spans multiple specialised fields. A generation ship could carry stockpiles of critical components, but eventually those stockpiles will be exhausted. Computers will fail, sensors will degrade, navigation systems will drift. Without the ability to manufacture replacements from raw materials, the ship becomes progressively less functional, generation by generation, until it can no longer navigate, communicate, or sustain its population. Consider the problem of materials science. On Earth, we mine metals, refine them, alloy them, and shape them. We have access to the periodic table, extracted from the crust of an entire planet. A generation ship carries only what it launched with. Recycling metal is possible, but each recycling process introduces impurities. Aluminum recovered from waste is not identical to virgin aluminum. Steel reforged repeatedly becomes brittle. Plastics degrade, their polymer chains breaking down with each heating. Over centuries, the very materials that comprise the ship weaken, becoming less reliable, less useful, less able to serve their purpose. And there is no planet to mine, no asteroid belt conveniently nearby. The ship must carry everything, forever. Even the structure of the ship itself is not immune. Radiation, micrometeorites, thermal cycling, and mechanical stress gradually degrade hulls, seals, and joints. On Earth, structures are maintained and rebuilt. On a ship travelling through interstellar space for centuries, there is no dry dock, no external repair, no replacement of aging infrastructure. The ship grows old, its bones weaken, and its passengers, generation after generation, inherit a vessel less capable than the one their ancestors boarded. Then there is the irreversibility problem, a psychological and logistical trap that tightens with every passing year. For the first decade, perhaps even the first few decades, turning back is conceivable. The ship could decelerate, reverse course, and return to Earth within a human lifetime. But as decades stretch into a century, as the ship travels farther and farther from home, the mathematics shift. Returning would take as long as continuing forward. The mission becomes irreversible, not because it is physically impossible to turn back, but because doing so offers no advantage. The people aboard are trapped, not by walls, but by distance and time. Every decision made in the early years becomes binding on all future generations. Those born aboard the ship inherit a trajectory they cannot escape, a destination chosen by ancestors they never knew, and a fate they cannot alter. And yet, despite all these challenges, the most damning realization is this. Even a generation ship the size of a small city, equipped with the most advanced recycling systems, the most redundant backups, the most carefully selected population, would still not be truly self-sufficient. It would be a slow-motion experiment in entropy, a race between system degradation and arrival at the destination. And if the destination is 100 light-years away, the journey could take thousands of years. No closed system, no matter how well designed, can sustain itself that long without external input. The second law of thermodynamics is patient, but it is absolute. Entropy always wins. The dream of a self-sustaining generation ship is not merely an engineering challenge. It is a confrontation with the fundamental laws of reality. We cannot escape entropy. We cannot create perpetual motion. We cannot build a system that lasts forever without degradation. And so, the generation ship, humanity's most romantic vision of interstellar travel, is revealed as an impossibility, not because we lack the will or the ambition, but because the universe itself forbids it. Closed-loop systems do not exist. Sustainability is a horizon that recedes as we approach, and in the cold void between stars there is no resupply, no second chance, and no forgiveness for failure. In the silence of space, aboard a ship that can never be truly self-sufficient, time becomes not a measure of progress, but of decay. Every day is a countdown. Every generation inherits a system slightly more broken than the one before, and the stars, distant and silent, offer no answers, only the indifferent vastness of a universe that does not care whether we arrive or perish along the way. We have travelled far in our imagination, crossing distances that stretch the limits of comprehension. We have witnessed Jupiter's storms, drifted through Saturn's rings, and contemplated the frozen shores of distant moons. But now, as our journey reaches its conclusion, we must face a truth both humbling and profound. The stars beyond our solar system are not destinations. They are eternal monuments to distance itself. And humanity, for all its ingenuity and ambition, may never leave this cosmic neighbourhood we call home. This is not a failure. It is not a limitation of our species' potential. It is simply the reality of a universe built on scales that dwarf even our grandest dreams. The distances are too vast, the energy requirements too immense, the time too cruel, the void too hostile. Every obstacle we have explored throughout this journey converges on a single, undeniable conclusion. Interstellar travel, as we imagine it, belongs not to the realm of engineering challenges to be solved, but to the realm of fantasy. The nearest star system, Alpha Centauri, lies 437 light-years away. With our current technology, reaching it would take tens of thousands of years, even with proposed technologies that push the boundaries of physics, fusion drives, antimatter engines, light sails powered by massive lasers. We might reduce that journey to centuries. But centuries are not lifetimes. They are epochs. Generations would be born, live, and die without ever seeing their destination, without ever feeling the warmth of a new sun on their faces. And even if we could build ships capable of sustaining life for such spans of time, the energy required would exceed anything humanity has ever produced. The fuel needed to accelerate even a small craft to a fraction of light speed would dwarf the total energy output of our entire civilization. We would need to harvest the power of stars themselves, constructing Dyson spheres or similar megastructures, just to launch a single vessel into the void. The mathematics are not uncertain. They are absolute. The universe has set the price for interstellar travel, and we cannot afford it. Then there is time itself, that most implacable enemy. As velocities increase toward the speed of light, time dilation becomes not just a theoretical curiosity, but existential crisis. Travellers aboard a relativistic spacecraft would age slowly compared to those left behind. They might experience decades while centuries pass on Earth. They would return, if they returned at all, to a world that had forgotten them, to families that existed only in history. The act of reaching for the stars would sever them from everything that makes us human, our connections, our shared timeline, our place in the continuous story of our species. Space itself is hostile in ways we can barely comprehend when we remain within our solar system's protective embrace. Beyond the heliosphere, beyond the bubble of charged particles our sun creates, lies true interstellar space. There, cosmic radiation intensifies. High-energy particles stream through the void unimpeded, capable of shredding DNA, destroying electronics, and slowly killing any living thing exposed to their relentless bombardment. Even travelling at immense speeds, a journey of centuries means centuries of exposure. Shielding heavy enough to protect against such radiation would add mass, and mass requires energy, and energy demands fuel, and we return again to the same impossible equation. The closed-loop life support systems required for multi-generational voyages do not exist, and may never exist. Every biological system leaks. Entropy cannot be reversed. Over decades and centuries, precious elements would be lost. Recycling would become less efficient, and the delicate balance required to sustain life would slowly collapse. Earth is not a closed system. It receives constant energy from the sun, maintains its atmosphere through planetary-scale processes, and has evolved over billions of years to support life. A spacecraft is a tiny bubble of artificial order, fighting against the universe's tendency toward chaos. It is a battle that, given enough time, cannot be won. We have examined every angle, pursued every theoretical possibility, and the conclusion remains unchanged. The stars are not forbidden to us because we lack intelligence or courage. They are forbidden to us because the universe is built on a scale that makes them unreachable. This is not pessimism, it is acceptance. It is the beginning of wisdom. But here, in this moment of acceptance, something remarkable emerges. A realization that transforms disappointment into wonder. Our solar system, the cosmic prison we call home, is not small. It is not limiting. It is vast beyond the capacity of human minds to truly comprehend. And within its boundaries lies not confinement, but possibility measured in trillions of lives. Consider our solar system not as a cage, but as an empire waiting to be built. 8 major planets, hundreds of moons, millions of asteroids, each one a world of resources and potential. The asteroid belt alone contains enough raw materials to build habitats for quintillions of people. The moons of Jupiter and Saturn hide oceans beneath their ice. Oceans that may harbour life, or could be transformed to sustain it. Mars, cold and barren today, possesses the basic ingredients for terraforming. Given centuries and sufficient technology, we could wrap that world in a thicker atmosphere, warm its surface, and watch as liquid water returns to flow across ancient riverbeds. Humanity could spread throughout our solar system not as explorers visiting distant worlds, but as settlers claiming new homes. We could hollow out asteroids and spin them to create artificial gravity, building O'Neill cylinders, vast rotating habitats with Earth-like environments contained within. These structures could house millions each, floating in space, powered by the sun, filled with forests and lakes and cities that orbit between the planets. The theoretical calculations show we could build enough of these habitats to house trillions of humans, perhaps even tens of trillions, each living in comfort, each with space to grow and thrive. Mining operations on asteroids could extract metals, water and rare elements without scarring a living world. The gravity wells of planets make launching materials expensive, but in the microgravity of space, moving resources becomes a matter of patience rather than power. We could build fleets of automated mining craft that harvest the wealth of the solar system, delivering materials to orbital foundries where they are transformed into new habitats, new ships, new infrastructure for our expanding civilization. The moons of the outer planets present their own opportunities. Europa, with its subsurface ocean, could become a research station where we study alien biochemistry and learn how life adapts to extreme environments. Titan, with its thick atmosphere and liquid methane lakes, could host floating cities, research colonies where we study weather systems that mirror Earth's hydrological cycle, but operate at temperatures hundreds of degrees colder. Enceladus, venting water vapour from its southern pole, could supply fuel and life support for missions throughout the outer solar system. Venus, despite its hellish surface conditions, could be transformed not through terraforming its ground, but through aeroforming its atmosphere. Floating cities could drift in Venus's upper atmosphere, where temperatures and pressures are remarkably Earth-like. These cloud cities could extract carbon from the thick atmosphere, slowly transforming Venus over millennia, while providing homes for billions in the meantime. Even Mercury, scorched and airless, holds value. Its proximity to the sun makes it ideal for massive solar collectors, arrays that could beam energy throughout the inner solar system, powering industry and habitation on worlds too distant to efficiently harness the sun's light. Mercury's extreme temperature variations and lack of atmosphere make it harsh, but they also make it perfect for automated industries that require neither comfort nor air. Our sun itself becomes not just a source of light, but the engine of our civilization. Every second it releases more energy than humanity has used in all of recorded history. Capturing even a fraction of that output would give us power beyond measure. Dyson swarms, collections of solar collectors orbiting the sun, could provide energy to sustain a civilization of trillions. The engineering challenges are immense, but they are not impossible. They do not require us to violate physics or discover new fundamental forces. They require only time, resources, and determination. The theoretical carrying capacity of our solar system is staggering. With the right infrastructure, with habitats built from asteroid materials and powered by solar energy, with closed-loop life support refined over centuries of development, our solar system could sustain a human population numbered not in billions, but in trillions. Some estimates suggest tens of trillions, others hundreds of trillions. The exact number depends on assumptions about efficiency and lifestyle, but the conclusion is clear. We have barely begun to fill our cosmic home. This abundance changes everything. The question is not whether humanity has room to grow. It is whether we have the wisdom to grow sustainably, to build a civilization that lasts not centuries but millions of years, spreading throughout our solar system, while maintaining balance with the resources available to us. Focusing our efforts on solar system development is not settling for second best. It is choosing the path that is actually achievable. Every mission to Mars brings us closer to establishing a second home for humanity. Every advance in asteroid mining makes space-based industry more viable. Every year we operate the International Space Station teaches us more about living beyond Earth. These are not small steps. They are the foundation of our future, the practical work of becoming a multi-world species. The dreams of reaching other stars need not be abandoned entirely. Perhaps in centuries or millennia, breakthroughs we cannot imagine will make interstellar travel feasible. Perhaps our distant descendants will find ways to bend the rules we believe are absolute. But we cannot build our future on perhaps. We must build it on what is real, what is possible, what lies within our reach. There is profound beauty in accepting our limitations. The philosophy of boundaries teaches us that constraints do not diminish possibility. They focus it. They give us direction. A painter limited to a canvas does not mourn the walls they cannot paint. They create masterpieces within the frame they have. Our frame is vast. It encompasses worlds we have barely glimpsed, moons we have never touched, resources we have barely begun to utilize. Being a single-star species is not a failure of imagination or ambition. It may simply be our natural state, the reality for most intelligent life in the universe. Perhaps the cosmos is filled with civilizations, each bound to their own solar system, each building their own empires around their own suns, each gazing at the stars and recognizing them not as destinations, but as distant companions in the great silence of space. This realization brings not despair, but peace. We are not trapped. We are home. Our solar system is not a prison, but a vast estate, filled with rooms we have yet to enter, landscapes we have yet to see, possibilities we have yet to imagine. Within these boundaries, humanity could flourish for millions of years, evolving, creating, discovering, and thriving under the light of our sun. The distances that seem so cruel, so impossible, become protective moats. They ensure that if we make mistakes, if we stumble in our development, we do not drag other worlds down with us. They give us space to grow, to learn, to become wise enough to deserve the cosmic stage we occupy. Our cosmic prison, examined closely, reveals itself to be a mansion of unimaginable size. To walk its halls would take lifetimes. To know all its rooms would require centuries. To fully utilize all it offers would occupy our species for eons. We stand at the threshold of this vast home, having barely explored its entry hall, and mistake our lack of progress for lack of space. The journey we've taken through this night, from Earth's orbit to Saturn's rings, has shown us both the magnificence and the boundaries of our solar domain. We have seen storms larger than worlds, moons that hide oceans, rings of ice that shimmer in eternal twilight. These wonders are not distant fantasies requiring impossible technologies to reach. They are here. They are part of our neighbourhood. They are waiting for us. As we drift now towards sleep, toward the quiet darkness that mirrors the space between stars, let this thought bring comfort. We are exactly where we are meant to be. Our sun, the star we orbit, the light that gave birth to our world and continues to sustain it, is not one star among billions we might visit. It is our star, the only star we need. Humanity's future lies not in escaping our solar system, but in fully inhabiting it, in transforming it from a collection of distant worlds into a true civilization, in building not just outposts but homes, not just visiting but staying, not just surviving but flourishing across dozens of worlds under one sun. The stars will remain distant, untouchable, eternal. They will continue to inspire us, to remind us of the vast universe beyond our reach. But they need not be destinations to have meaning. They can be reminders of our place, guides in the darkness, silent witnesses to the civilization we build here in this small corner of the galaxy. Our solar system is humanity's forever home, and that, when truly understood, is not a limitation. It is a gift measured in trillions of possible lives, in millions of years of potential history, in wonders enough to occupy our imagination until our sun itself grows old and red. We need not leave to find greatness. We need only look around us, at the worlds that orbit nearby, at the resources floating between them, at the energy pouring endlessly from our star. Everything we need is here. Everything we could become lies within these boundaries. Sleep now, knowing that our cosmic home, vast and filled with possibility, will still be here when we wake. The journey continues not outward to impossible stars, but inward, into the heart of our solar system, where humanity's true destiny patiently waits. And so we return from the depths of contemplation, carrying with us the weight of cosmic truth. We have journeyed through the barriers that contain us, not as explorers charting new frontiers, but as inhabitants understanding the boundaries of our eternal home. 6 walls surround humanity's prison, each more insurmountable than the last. First, the tyranny of distance. Space between stars is not merely vast, it is incomprehensible. Light itself, the fastest phenomenon in existence, takes years to cross the gulf between our sun and the nearest stellar neighbour. Human vessels, crawling at fractions of light speed, would require millennia, epochs, entire spans of civilizational time to traverse what light accomplishes in a handful of years. Second, the energy problem. We have calculated the requirements and they mock our ambitions. To accelerate even a modest spacecraft to velocities necessary for interstellar travel would demand more energy than our entire civilization produces in years, perhaps decades. The laws of physics do not bend to human desire. They stand immovable, indifferent to our dreams of the stars. Third, the hostile void. Radiation saturates the space between worlds. Cosmic rays and particles accelerated to unimaginable speeds tear through matter itself. Beyond our sun's protective bubble, space is not empty, but filled with invisible violence. Shielding sufficient to protect human life would be so massive, so heavy, that propelling it becomes its own impossibility. The universe, it seems, was not designed with travellers in mind. Fourth, the time dilation paradox. Even if we could approach the speed of light, physics becomes cruel in new ways. Time splits between traveller and home. Seconds for the voyager become years for those left behind. To journey to another star and return would be to arrive in a world where everyone you knew has aged decades or died entirely. You would become a ghost, haunting a future you helped create but can never truly inhabit. Fifth, the sustainability impossibility. No closed system is perfect. Every breath exhaled, every calorie consumed, every machine that fails represents entropy advancing. On journeys lasting generations or centuries, even the smallest inefficiency compounds into catastrophic loss. We cannot carry enough resources, cannot recycle perfectly enough, cannot maintain systems indefinitely against the slow decay of all things. And sixth, the psychological reality. Humans are not made for the endless night between stars. Our minds evolved under open skies, our bodies shaped by gravity and daylight. Confinement in metal vessels for lifetimes breeds madness we can barely anticipate. We are creatures of Earth, and the cosmos reminds us of this truth with every light year that separates us from home. These are not challenges to be overcome with ingenuity or determination. They are laws, fundamental and eternal. The universe has set boundaries around humanity, and those boundaries are the edge of our solar system. But perhaps this realization is not a tragedy. Perhaps it is a gift. Our solar system is vast beyond human comprehension. It contains worlds we have barely touched, moons hiding oceans beneath ice, asteroids rich with resources that could sustain civilizations for millions of years. The time it takes to truly explore even our own stellar neighbourhood stretches across centuries. We have visited Jupiter, drifted through Saturn's rings, glimpsed the ice giants in the outer dark. Yet we have only scratched the surface of what lies within our cosmic home. Humanity's future is here, among these 8 planets and countless smaller worlds. Our descendants may walk on Titan's shores, mine the asteroid belt, build cities beneath the ice of Europa. They may terraform Mars, harness the energy of the sun itself, and spread throughout every habitable corner of this system we call home. This is not confinement, it is inheritance. The solar system is humanity's forever home, and there is profound peace in accepting this truth. We are not meant to wander the galaxy. We are meant to flourish here, in this pocket of warmth and light carved from the infinite cold. To understand our limitations is not defeat, it is wisdom. Thank you for joining this journey through the terrifying, beautiful realities of cosmic distance, for travelling with us through the void, past Jupiter's storms and Saturn's frozen rings, to the edge of what humanity can ever truly reach. If you found this exploration fascinating, if these thoughts brought you peace or perspective, or if this video accompanied you into restful sleep, please take a moment to like this video. Your engagement tells us that contemplations like these matter, that there is value in understanding our place in the universe. Leave a comment below telling us where you're listening from. Perhaps you're in a quiet room as night falls, Perhaps you're watching dawn break over your city. Tell us your corner of Earth, or if you're feeling whimsical, your corner of the solar system. This community spans the globe, and we would love to know where these words find you. Subscribe to this channel for more science content designed for deep contemplation and peaceful sleep. We explore the cosmos not just to understand it, but to find our place within it, to transform the vastness into something comprehensible, even comforting. In our next video, we will explore the terrifying reality of rogue planets, worlds cast out from their stars, drifting alone through the galactic dark. Until then, rest well, dream deeply, and remember that home is closer than you think. We are here, together, beneath the same sun, and that is enough.